Good afternoon, everybody out there on streaming land. This is a review session today for the first exam in Math 105, Mathematical Thought and Practice. So we're going to spend our time together on the live stream today over the next hour looking back at the topics we've been talking about for the past 3 weeks and just getting a chance to look at them once again with a fresh set of eyes to help you be prepared for the exam that's coming up this week. So broadly speaking, the topics we're going to cover today include the basic elements of set theory. So what are sets? What are subsets? What are the cardinal numbers of sets? How do we count their elements? Notions about Venn diagrams, so how to use Venn diagrams, especially as we start to get diagrams with 3 sets or maybe even more than 3 sets, and how to implement Venn diagrams into reasoning about applied problems, such as problems regarding survey data. And then the last third of the material on this exam regards propositional logic. So a little bit about what distinguishes propositional logic from other kinds of reasoning, and how do we take propositions and stick them together with various conjunctions, connectives, and so forth, and assess the truth value. And in particular, the big question in the third topic, the big question that we want to answer about logic, is how do we recognize a valid argument in logic when we see one? And what are some ways in which arguments in logic can be shown to be invalid? So what I especially want to do with that review is take the opportunity to talk a little bit together about a topic we haven't gotten to talk too much about together, and that is how do we use diagrams to help assess the validity of a logical argument. It's very much like Venn diagrams, but we give them a different name when we use them to assess logical claims. We call them Euler diagrams, interestingly enough. So that's kind of the 3 main priorities that I have for our review. So basic elements of sets and subsets, basic set theory, Venn diagrams, and set operations. And we had a request in the Slack channel for us to especially talk today about how do you use a Venn diagram to assess the equality of 2 sets. So how do we reason about whether 2 set operations give us the same result one way or the other? So I'll be sure to talk about a proof along those lines as well. Let me get our chat channel ready to go here. And then again, the third topic that we want to talk about is how do we use diagrams, especially to assess the validity of a logical argument. So we'll get a little chance to talk about what are called Euler diagrams today. A little trouble with my tools here. There we go. Scoot this over. And sorry to those of you watching this real time, I've just got to make a quick adjustment to make sure I've got the right chat window showing up. There's what I want. Okay, excellent. So again, the third topic is argument validity. And using what's called an Euler diagram. It's like a Venn diagram, but for logic instead of for sets. So what I'll do is I'm going to pull some examples of some problems in each of these 3 areas, and then together we'll talk through the solution strategies and methods and things to think about when we're working on each one of these types of problems. So let's kick off the festivities. I want to go directly to the question that we received in the chat channel a few minutes before we went live, just to make sure that we get a chance to address it. And that question is, how do we use Venn diagrams to verify the equality of sets? So this is admittedly one of the more challenging topics in the sort of advanced bits of set theory. Venn diagrams and set equality. So let me go and pluck a question that we can use, a problem that we can use to illustrate a solution strategy for this. If you'll indulge me to just get into my little bag of tricks over here on this side. Yeah, so here's one that I like. So I kind of want to do this in 2 parts. I first want to talk about how to pick apart logical notation to describe a set, because that I think is the sub-skill that makes this particular set of material the most challenging. So I'm going to start with the following problem. Let me transfer it over into my canvas here. So in this problem, we're given a universe, so a set with some elements that are going to make up our universe, and then we're also given three subsets, so three sets whose elements live within that universe. And then our job is to say something about a set operation that involves those elements. Why am I having issues here finding the right place to receive this? Try one more time. All right, why don't I just do this? Drop it into Dropbox, and then I'll bring it back out. So the hardest part about doing this live is that sometimes it takes a few seconds to get everything where it needs to go. And that little ding is the Twitter notification that we've just gone live. So probably you've already noticed that if you're watching at the moment. And just give me one more second here to get this problem ready to hit the canvas here. Okay. So here it comes. We're given a universe, and we're given three subsets inside of that universe. And then we're asked to figure out what are the elements of a particular set that's combined in that universe from some set operations. So here it is. Here's the problem. We're given a universal set. It contains elements that we call A, B, C, D, E, F, G, and H. And then we're given three subsets, A, G, and H, B, G, and H, B, C, D, E, and F. Each of those subsets have names. And our first job is to figure out how to think about this funny combination of set arithmetic, set operations. What subset are we actually talking about? What elements belong to that set? I'll confess, I'm a professional mathematician, and I have been for 10 plus years at this point. I still can't do any problem of this type without drawing a Venn diagram. So without getting it down in a visual format that I can use to understand what's really going on. So that's going to be my go-to strategy as far as step number one in understanding what's going on here. So let's do that. You'll notice that since we're kind of given this U, the universal set, at the beginning of the problem, typically in our Venn diagram, that's the set which is indicated by a rectangle drawn around the whole thing. So it's going to tell us what all the animals in our farm are, and then we're going to organize those animals into some smaller sets afterwards. So since I have three sets, A, B, and C, that are all a part of the question here, that means that I'm going to want a three-set Venn diagram to help organize this information. So I'm also going to add in these three sets here in the middle of my rectangle, call them A, B, and C. And now, of course, our job is to figure out where all of the various elements that are represented here, where they all fit. So let's start by, well, one of the ways that we can start. So this may be, I don't know if this is a way that you're going to latch onto to do these problems, but remember the first rule of any Venn diagram. The first rule of any Venn diagram is never double count anything. So any element that we put into this diagram should appear in exactly one of the regions of this Venn diagram. I can't put anything in more than one spot. And one way of ensuring that that doesn't happen is by first just throwing everything into the pool and then going back and removing double counting. So I kind of want to model that process right now for coming up with this Venn diagram. So what I'll do is start by taking my universe. So it consists of these 8 elements. So the cardinal number of U here is 8. And I'm just going to draw in those elements into my universe. I'm going to put them inside of U, but I'm not going to put them inside any of these other 3. So I'm just going to kind of draw them out here. A, B, C, D, E, F, G, H. So just to get them somewhere in my diagram. Then I'll do the same thing with the sets A, B, and C. So for the set A, it has the elements A, G, and H. And I'm just going to naively just throw them right here into the set A inside of my diagram. Same thing with B. So B has elements B, G, and H. And then the same thing with C, has elements B, C, D, E, and F. Why I kind of like this method for attacking a Venn diagram is that you don't do too much thinking up front about where to put things, and it ensures that everything that belongs to these sets ends up landing somewhere on the diagram to get us started. So I've thrown all the elements into my diagram that are fit to throw. Now I have to appease rule number 1 of a Venn diagram, which is don't double count any element. Every element on this diagram needs to appear in exactly one location. And you can tell from what's on the screen that already that's not being satisfied by the diagram that I drew. A, for example, appears as an element both here and also there. Right? So that's a problem. That means that we can't write it in both of those places. We can only write it in one of those places. And so the decision rule here to remove double counting is to put every element in as deep of an intersection as possible. So move everything that's necessary toward in the direction of the intersections, which, by the way, is the opposite of the way that we worked survey problems. When we had survey data and we were putting it into a Venn diagram, we worked from the inside of the intersections toward the out. And here, I'm trying to remove double counting by working from the outside in when I'm using this method. So what I mean by that is I have to break the tie between writing A as an element outside here in the universe and writing it as an element of A. And to break that tie, I want to go as far inside of my circles as possible. And that means I need to take the A away from the outside of these sets and leave it in here. And now that it appears in only one location, now I know that that's where A belongs at the end of the day. So I'm going to kind of draw, let me just draw a little marker around A to indicate that now I'm done with A. I know A is going to live in that region of the Venn diagram because I've confirmed that it doesn't belong to any of the other intersections of A with anything else because it's not listed over here and it's not listed over there. So that's where A belongs. What about B? And B has a bigger problem because it's appearing in 3 locations, right? It's a part of the universe, it's also a part of the set B, and it's a part of the set C. So as we're working towards intersections, we know that B should not be listed as something outside of the sets A, B, and C. So I'm going to remove it from that outside region. But now B is still showing up in 2 separate places, an element of B and an element of C. And so again, try to move that towards the direction of deeper intersections. So if it belongs to both B and C, that means I really ought to be putting it right here, where the circles for B and C overlap. So rather than having it here or there, I'm going to put it there. And now, if somehow B were also listed over here as an element of A, then I would have to move it one step further in to the triple intersection. But it's not, so that's where B ends up belonging permanently, right, in my Venn diagram. And so that same process we can use to resolve the ambiguity about C. So C belongs definitely in the set C, but not outside. D is listed in 2 locations, also the set C and the universe. So where it belongs is in the set C. So that's where C belongs, that's where D belongs. Likewise with E, it's outside and it's in the set C. So we'll take it away from the outside, and that's where E belongs. Likewise, F is outside and it's a part of the set C. So where it belongs is inside of C. G is on the outside, but it's also a part of A and B. So we'll take it away from the outside and we'll put it in the region where A and B overlap. But since it's not an element of C, that means we don't have to move it in here into this triple intersection, so that's where G ends up belonging. And finally, H, same story as G. It's a part of the universe, but it's also a part of A and B, so it doesn't belong out here. It doesn't belong in these regions because it's in common to both A and B, so we'll move it into the same intersection of A with B that we put G in a second ago. There's H. And again, because H doesn't belong to C, we don't move it into the triple intersection. So that was step one in this problem, is just getting the Venn diagram set up so that each of the elements in my universe appears in one and only one location. All right, so now let's get to the end of the question, which asks us to find the set. And if I were clarifying this question, I might also say something like find a roster for the set. In other words, what I'm kind of asking you to do here is to list all of the elements that belong to this set. But I mean, that's no simple task, because the set here is created through a bunch of set operations. So what we have to do is take these set operations apart to figure out what set we're really talking about. And this is going to be a feat of notation. Notation, of course, is one of the places that's easiest to struggle if you don't speak the language of mathematics. And mathematicians don't speak the language of mathematics. They speak the language of English, or whatever language they happen to speak in. So for everybody, there's a process of taking apart what are these set operations telling us to look for. So following our order of operations like guidance, right, and our order of operations guidance, what it tells us is that we should first start by looking at what's inside of parentheses and then working our way out. And then also, we should look at multiplications before we look at additions. And in set theory, what that means is we should look at intersections before we look at unions. And if we do that, then we're going to work our way out in this problem. So following that guidance, the first thing I want to do is look inside of each of our sets of parentheses. So C complement intersect with A, which, by the way, you'll notice this problem is using slightly different notation for complement. This came out of a different textbook, so my apologies for that. I'll be sure to use in our exam the notations that we're accustomed to. So C complement intersected with alpha, or sorry, with A. And then the other thing inside of parentheses is C complement intersected with B complement. So I want to find what are both of those sets. And then once I've found both of those sets, the job is going to be to union them with one another. So that union is happening last here. So the union. So whatever answers that we get for the rosters of these two sets in parentheses, we're going to take the union of those two sets, and that's going to give us our final answer. So our final answer is going to be here. So it's that process of laying out my solution strategy, my problem-solving approach. I encourage you, even when you're just working on these problems on your own, when you're doing scratch work on the back of a napkin, or wherever you're sort of getting your first ideas down onto the page, try and organize your thoughts in a way like this. It'll really help out in the long run. Otherwise, if I just look at this whole thing, it just looks like one big jumbled up together mess of notation. But when I can take apart the pieces, and the parentheses kind of tell us how to identify pieces, individual pieces to take apart, when I can take those pieces apart, it narrows down my problem and helps me to solve smaller problems, which are generally simpler. So, all right, let's get into it. So for the set C complement intersected with A, that's going to be where we start our search here. I'm going to look at two things. I first want to look at C complement. And remember that complement is the set theory equivalent of the logical negation. And what I mean by that, C complement consists of everything which does not belong to C. So if I want to know where C complement is in my diagram, I want to shade everything which is outside of the set C. So C complement is, I kind of shade it like this, everything which lives outside of C. So that's C complement. Meanwhile, A is exactly the circle that we've labeled A here on this diagram. So here's A. It's everything inside of that circle. And I'm being asked to find the intersection of C complement, which I shaded in purple here, with A, which I've shaded in yellow. And if I'm looking for the intersection, I'm looking for where those two sets overlap with one another. And those two sets overlap with one another in this region. So it's definitely got to be outside of C, but it also has to be within A. And so that intersection is this region right here. It's where the stuff which is outside of C overlaps with the stuff which is inside of A. I've noticed that some of you, when you solve problems like this, will, I think a good idea, translate into English. So, not in C, and in A. Right? The not in C is the translation of C complement, and is the translation of that intersection, and then A after this. Right? So looking at my Venn diagram, I can see that a roster for that set, the elements we can write in that set, consist of A. A belongs in that set because it's an element of A and it's not an element of C. And then likewise for G and H. Right? They are elements of A and they're not elements of C. So there's a roster for C complement intersect A. I'm going to just take a moment and clear off my diagram real quickly just so that I can use the diagram again without getting too cluttered. But the great thing about video is if you wanted to relive that reasoning, you can just rewind a minute or two and we can get back to that. All right, so we've got our first set figured out. How about our second set? C complement intersect B complement. So once again, C complement is going to consist of everything not in C. So I'm going to shade everything outside of the C circle. There's my C complement. But now I need to shade also everything that's outside of B. So B complement, let's get that shaded as well. So everything that doesn't belong to the set B. Right? And I'm again taking the intersection of those two sets. So I want to look for where this orange shaded set and this red shaded set overlap one another. If we wanted to write that in words, once again, we could write that we're looking for the elements which are not in C and also not in B. That's what we mean by C complement intersect B complement. And if I were to shade that region on this diagram, I would be shading, well, I'd be shading, it turns out, a ton of stuff. There's a ton of places where this overlaps. But most notably is where I'm not shading. I'm not shading anything that belongs to the set B, and I'm not shading anything that belongs to the set C. So here is what this set is going to look like. It's all this pink area. It's everything in this diagram except the union of the sets B and C. So if I find a roster for that, that roster is not going to include anything which is inside of the set B or the set C, but it is going to include the element which is in neither of those two sets. And therefore, the roster for this set is only the element A. So let me declutter my diagram one more time so we can use it again later. Okay. And so a roster for this set, it's a single element set, and the only element in that set is the element A. So we've got each of these two pieces. Now, what do we do with those two pieces? We have to take a union. A union of this first set with this second set. And how does a union work? A union of two sets consists of all the elements that belong to one or both of the sets. So we're taking all the elements from those sets and we're throwing them all into one big bucket, and that bucket is called the union of those two sets. So since A, G, and H are being contributed by the first set here in the union, A is being contributed by the second set. If I throw all those elements together, I might write it like this: A, G, H, and then also A. But set membership is a logical proposition. That means that membership in a set is either true or false. It can't be true multiple times over. Right? Once an element belongs to a set, it belongs to the set. And if we list it more than once, then we don't need to list it more than once, is I guess my point. So listing A twice, as I've done here, is redundant. I get the same set if I list A only once. And so that's what I'll do. When I take the union of these two sets, the A ends up being an element of the union because it happens to belong to both, but G and H are also elements of the union because they belonged to one of these two sets. And so the final answer for this question would be that this nasty bit of set notation ends up having the roster AGH. So let me slow down because we've been working this example for about 15 minutes. I just want to check in and see if there are questions in the stream on how we did this so far, because I want to take this example next and use it to illustrate thinking about set equality in three-set Venn diagrams. But are there any questions? Post them either up on the Twitch stream chat or post them up into Slack. And I'm going to move on in just a minute from this example to an example that illustrates a method of set equality. So let's do a problem about set equality. I'm just going to write one on the fly here. So a problem of set equality is usually posed as just that, right? It's usually posed as the question, if I give you two expressions using set operations, do those two expressions describe the same set or not? So here's an example. How about A intersected with B complement union C, and A unioned with B union C complement, quantity complement. So what am I doing here? I'm giving two examples of set arithmetic, and I'm asking, when I form these two expressions using set arithmetic, am I guaranteed to get the same set when I do these two things or not? And to answer that question, we first have to rewind a little bit and think about what does it mean for two sets to be equal. Generally for numbers, we understand what it means for numbers to be equal, right? That they describe the same quantity, right? The number 8 and the number 8 are the same because they both count sets that have 8 elements in them. But for sets, we have a little bit higher level of sophistication in thinking about what it takes for two sets to be equal. So let me get that established up here at the top. If I have two sets S and T, then to say that those two sets are equal is a very strong statement. It's more than just the statement that says these two sets have to have the same number of elements in them. Rather, not only do the numbers of the elements in S and T have to be the same, the cardinal number, but also the elements themselves in S and T have to be the same as one another. So how we can say that is as follows. Every element of S is an element of T. And every element of T is an element of S. So both of those statements have to be true. Every element which belongs to one of the two sets also has to belong to the other one. Another way to say this is S and T are equal if it's true that both S is a subset of T and T is a subset of S. Right? So that's what we mean by set equality. The elements in the two sets have to be exactly the same as one another. So in this question, what we're asked to do is take these set expressions and figure out whether they are always guaranteed to describe the same set. If I were somehow to simplify these expressions in set algebra, would they give me the same set necessarily? So as with our previous example, Venn diagrams are really the best way forward. Because if you can get a Venn diagram on the page that adequately captures each of these two sets, then all we have to do is compare the results and see whether or not we've indicated the same regions on our Venn diagram in both cases. So what I'm going to do here is get a Venn diagram down that describes the first set that we have listed up there at the top, another Venn diagram that describes the second set, and then we'll just compare the two. Maybe one of them is a subset of the other. Maybe they're exactly equal. Maybe neither is true. So there's sort of the plan. So let me highlight my first set here, A intersect B complement union C. That's the one that we're going to try and shade over in this first diagram. And then the second diagram, we'll want to shade this one. Okay, so I want to shade the regions which correspond to each of these combinations of sets first, and then just compare the two. So again, following the order of operations, the first thing we're going to want to do is look inside of parentheses and say, all right, inside of my parentheses here, B complement union C, let's get that set shaded first. So maybe I'll take out my pink highlighter here and say, I'm going to try and highlight this set here in pink, B complement union C. Well, what's B complement? B complement is everything outside of B. So I'll start by shading everything outside of B. Draw my little sun here. But then I'm supposed to take the union of that with C. Now, since I'm taking a union, that means that I'm not looking for just where those two things overlap. I'm looking to just stick together all the elements of B complement with the elements of C. So I can finish shading all of B complement because I know that's going to be a part of my union. Hopefully this is all legible out there on the stream. So this pink thing that I've shaded here is B complement. But now I'm supposed to union that with C. So everything which belongs in C also has to be a part of my final shaded set here. Some of C already is. So this bit of C has already been shaded. But the bits of C that aren't yet shaded, we will have to add. So this little crescent there in the middle also has to become a part of my final set. So when I union together B complement, which is the pink shaded area, along with C, which is the orange shaded area, then my final answer, which I have to shade in brown here, my final answer is going to consist of all of this stuff, including that crescent there in the middle. So the first set of the two that I'm supposed to assess for equality, when we shade it here, it's going to consist of everything I've shaded here in brown. Is going to be B complement union C. And I almost did a common error that a lot of people do in this, and I almost forgot that I still have one more piece in my notation to satisfy. I have to intersect this with A. A being this set right here, right? This circle. So now I need to find out where this overlaps with A. And so that then will be my final shading. A intersected with that. So where does this brown set overlap with the A circle? That's going to be what I shade to finish my reasoning here. And so that means I'm just going to end up shading those areas of the A circle which I've colored brown previously. And so this red shading is now my final answer for that first set. A intersect B complement union C. In our first example, we were talking about how to verbally take apart notation just to reinforce why it is that we've shaded this area. So let's do that real quickly. We're talking about elements which are in A, and also they are not in B, or they're in C. Are in C. So for example, an element over here in this region is going to belong to the set because it belongs to A, and also it doesn't belong to B, for example. an element here in the triple intersection belongs because it's in A and it's in C, and so it satisfies this portion of my union. So these three regions taken together is what we get when we finish out this notation. So this process, it takes a while to get accustomed to. Shading the right regions, choosing the overlap, or choosing to glue things together in a union, and so forth. We'll see that really clearly, I think, in this next example, because we have even a little bit more going on with this notation. Let's figure out which regions in the Venn diagram we want to shade to assess this. So again, order of operations, let's start inside of my parentheses. Get my pink highlighter out again, and try to figure out how to shade B union C complement. So B, first of all, is of course this B circle. So I'll just kind of start by shading out my B. And now I have to take the union of that with C complement. And C complement is everything outside of the set C. So I'm going to shade outside of my C circle. So the union of B with C complement is going to include all of C complement. And it's also going to include all of B. And so what I end up getting when I take that union is all of these regions. So everything that I've shaded here is a part of what we're calling B. That's kind of hard to see, sorry. Let me write that in black instead. What I've just shaded is B union C complement. But now, as I think order of operations, the next thing I'm going to do is work my way out and notice that when the next thing I'm doing to this is I'm taking the complement of the thing that I just shaded. And that completely changes the ballgame, right? It turns it on its head, because what I want to be shaded after I do this operation is exactly everything that's not shaded right now. So the shading and the empty spaces are going to trade places when I apply this complement. So B union C complement is going to be a shading of just this region and that region. So just those two. So now we traumatically erase all the shading that I have here. Whoops, I've also, yeah, I can draw it back. Don't want to lose my universe here. But yeah, so now I just want to shade this region and that region. And this thing that I've shaded now is B union C complement complement. Okay. So what's my last thing to do? My last thing to do is take the union of that with A. A is this circle here. Taking the union means that I want to glue together those two sets, include all the elements that belong to one of them or the other. And so I'm going to add in my A in union with this thing that we already had. And now there is my finished set. This is going to be A union with B union C complement complement. Yikes. This is all the elements of my universe that either belong to A or they don't belong to the set which consists of the elements of B together with the elements not in C. Yikes. Rather than write that down, I'm just going to write down my finished answer here in notation. A union B union C complement complement. So we've done all the hard work now of figuring out how to sketch a Venn diagram for each of these two sets of circumstances. Put my universe back in here just so that we have a comparable picture. And so now the only question that we're left with is, are these two sets equal? Well, they're equal only if we've shaded exactly the same regions in both of these Venn diagrams, because those are the only cases in which every element of one is guaranteed to also be an element of the other. And that's not the case. For example, if I have an element here in the intersection of A with B, but not an element of C over here on this diagram. On this diagram, that region is not shaded. Over here on this diagram, it is. So there's a disagreement. And as soon as we have a disagreement, we can guarantee that these sets are not equal. So I'm just going to put a not equal to sign in the middle here. There are other places where we can come up with disagreements also. Actually, there's just one other place where we can come up with a disagreement. And that is over here in this region. I'm going to write it as a dagger. Okay. If I have an element which belongs to C but not to A or B, then it's included in this set, but it's not included in the red set that I've shaded over here. So there's another point of disagreement. But it only takes one disagreement for us to be able to conclude these two sets are not equal to one another. Moreover, we also can't conclude that either one of them is a subset of the other, because all the regions on the left here, well, let me pause there for a second. Every region that I've shaded on the left is also shaded over here on the right. Every element from this region is also an element in this set. Every element from that region also counts. Every element of this intersection in the middle region also counts. And so the only disagreements are disagreements where things are shaded on the right that are not shaded on the left. This region here is shaded in this set on the right, but not on the left. This region here is shaded in my final answer on the right, but not in my final answer on the left. And so what we can conclude more specifically about these two sets, they're not equal, but they do have a close relationship with one another. Namely, the set on the left is a subset of the set on the right. Because every region which I shaded on the left, every shaded region over here is shaded here on the right. So these two sets are not equal to one another, but the former is in fact a subset of the latter. These problems are no picnic. I really think they definitely are the most challenging problem types that you encounter when we're working with sets. So if you're really looking for a class of problems that's going to show you very clearly whether you've understood basically everything that there is to understand in our set theory, our 2 weeks on set theory, these are the kinds of problems that will do it. And I'll say that, you know, most of you watching this are not math majors, but even math majors need to slow down their reasoning and really think through these things carefully, because these are, I mean, really, this is a form of mathematical thinking that even math majors are often not accustomed to until they really get a lot more expertise in mathematics under their belt. And again, what I think is striking about this is that there are no numbers showing up here. This is purely, thinking about sets and logic is purely a logical reasoning exercise. And so it's a kind of mathematical thought that you probably haven't spent a lot of time in your previous math classes thinking about. So if you're not picking this up immediately, that's natural. And it's also why in our class we have plenty of opportunities for you to demonstrate that reasoning throughout the semester. So these are great practice problems for the exam, and you can definitely expect this kind of reasoning to show up on the test when we do it later in the week. So let me pause here for another half a minute just to check and see if there are questions in the stream that you want to put up about the example that we just did. After this, we're going to go on and do an example of assessing the validity of logical arguments to close out our stream today. But first, what questions, if any, do you have about this solution? Let's talk about argument validity. In a very real sense, this is the promise of logic, right? The promise of logic is supposed to be that we should be able to assess when somebody makes a logical claim based on a logical thought process and based on logical evidence. When somebody makes one of those claims, we should be able to assess whether that claim is true or false. Because if their claim is a logical proposition, then it must be either true or false. It must be either provable or falsifiable, right? And assessing an argument for its validity is at the heart, it's at the core of what logical reasoning is about. If you've had a course in logical reasoning, say taught in a philosophy department in the past, such as our Bridgewater State majors are all, not just majors, all of our students are required to complete a logical reasoning course as part of their general education requirements. You probably spent quite a bit of time assessing the logical validity of arguments that make claims to logical truth. So we're not spending a ton of time on it this semester because most of you have probably already gone through this before. But I want to look at a couple examples together today of assessing argument validity using the tools of our course. And in particular, I want to introduce a particular way of diagramming out an argument in order to assess whether it's of a valid form. So when we talk about formal logic, the word formal there doesn't mean that it's wearing a black tie and a bow tie or whatever. The word formal means related to form. So we're assessing the weight of an argument based on whether the form of the argument is appropriate, whether it's a valid form, rather than whether it's true or false. So when we're assessing the validity of an argument, we're not necessarily saying that that argument is true or false. We're saying that its conclusion follows from its premises. So that's what I'd like to do next here.
Hi.
So let me just grab a copy of this problem, and we'll put it onto our template for today. Okay, so I screwed this up before. I think I know how to do this now. Add in one more step. Sorry. See my computer screen behind the scenes here. Pay no attention to the wizard behind the curtain. Okay, and now if I do this, now it should be a little bit quicker. Send it over to my iPad. It should show up in my photos. No? Is it still not cooperating? Let me try one more time. Okay, I think I can do this just by going here and share with AirDrop. Cancel. Share it across. All right, I'll be shocked if this doesn't work now. Yeah, excellent. All right, we are in business. So our job is to assess the validity of the following logical argument. So the argument is, all thefts are immoral acts. So anytime you steal something, it is an immoral thing to do. So that's step one in our premises. Step two, some thefts are justifiable. So this is the classic person stealing a loaf of bread for their starving family. Maybe we accept as a premise that some thefts are justifiable. The question is, do those two premises necessitate the conclusion in this last statement, therefore some immoral acts are justifiable? So this is philosophy. Now we are doing philosophy. So let me, first of all, let me give these propositions some notation. If I call them P, Q, and R, okay, then what we're really asking when we're asking you to assess the validity of this argument is, if we accept the two premises, if we accept that P is true and Q is true, and we don't have to accept those things, but that's the thing about assessing the form of an argument, is we're going to agree to accept those two premises as true. Then the question is, must R also be true? Right? That's really the validity question. So we can argue, and we won't argue in a mathematical thought and practice course, we can argue whether or not it's true that all thefts are immoral acts. Right? That sounds like a great question for a philosophy or a criminal justice or a political science kind of course. Same thing with some thefts are justifiable. This is a great question. This is a theme even in a literature class. We can talk about whether or not these are true. But those are not our concern. Questions about the truth or falsehood of these propositions is not an issue for us. Our job is to assess the form of the argument, which is to say, if we do believe that P and Q are true, then must we accept that R is also true? Do the truth of P and Q necessitate the truth of R? So another way to write that as a logical form is to say, if we accept that P and Q are both true, so P and Q, must it follow that R is true also? So using the logical notation that we built up over the last week or so, remember, oh, I'm sorry, I screwed this up. Typo. P and Q. If we accept that P and Q are true, if P and Q are true, then is it true that R is true? That's what we have to figure out. All right, so now we know what the goal is, what we often call the burden of proof. I call it the burden of proof. It sounds very legalistic, but I like to think of that as what we're doing, right? Our burden of proof is to say, are there cases in which P and Q are both true, but R is not? So what I want to do, as the statement of this problem is asking us to do here, is to use a diagram to get at a way of depicting this problem. So what I want to do is key in this problem on a couple of sets. And why I like this is that it ties us back to the set theory arguments that we've been making about sets in the first phase of the course. Set theory and logic are intimately related one to another because set membership is a logical proposition. And so conversely, we can often frame logical propositions as propositions about set membership. And that's exactly what I'm about to do. Because our arguments here have to relate to three things. First of all, we have thefts. Second of all, we have immoral acts. Third of all, we have justifiability. So maybe I'll call them justifiable acts. And so what I'm going to do is I'm going to think of these three things as being elements of sets. So A is the set of all thefts. Every theft that has ever happened in the course of human history or ever will happen in the course of human history. B, likewise, is the set of all immoral acts that have ever happened in the course of human history or ever will happen in the course of human history. And finally, C, the set of all justifiable acts. Everything in history that has ever been justifiable for whatever agreed upon definition of justifiable we select. Again, this is not the place to debate those definitions. Whatever the definitions are, as long as you and I agree on them, we can both assess the validity of this argument and come to the same conclusion about whether the argument is valid. Okay, so what this question is really asking me to do is to come up with a way of relating these sets one to another to see if there's a possibility that the first two of these premises can hold while the conclusion does not. All right, so let me get my three-set Venn diagram template onto the page. Right. So here in the set on the left, the set A, we're going to have our set of all thefts. So let me shade that blue. So there's my set of all thefts. B, the set of all immoral acts. And C, the set of all justifiable acts. Shade that with some red. Here they are. So here's my three sets. Now that I have my three sets set up, what I want to do is first grant my hypotheses. Grant that P is Q and grant that Q is true. Mathematicians will say assume. Assume that P is true and assume that Q is true. And what I want to do is I want to use that information to change my Venn diagram a little bit. So here's what I mean. Let's grant that all thefts are immoral acts. That means that any element of A, the set of all thefts, is automatically an element of B, the set of immoral acts. So what this first statement is really saying, this logical proposition that we call P, is it's really saying that A is a subset of B. The set of all thefts is a subset of the set of all immoral acts. And so in my Venn diagram, what I want to do is I want to cross out everything which could belong to A which does not in the Venn diagram belong to B. So every part of A which is outside of B, I want to get rid of right now. So I'm going to do that just by erasing part of my diagram. I'm going to erase those parts of A which are outside of the set B. And so now, the picture that I'm trying to have emerge here, this is going to get a little bit messy before it gets cleaner, so bear with me for a minute or two here. The picture that I have now is that A lives entirely within B. Right? Because according to the first of these premises, every theft is an immoral act. So if I find a theft, it has to live both in the set of thefts, but it also has to automatically reside in the set of immoral acts, if we're granting the premise that all thefts are immoral acts. And we are granting that premise because that's part of how we assess for validity. Okay. So now we've granted the first proposition. What about the second one? The second one says some thefts are justifiable. What that means is that some of the things that belong to A also belong to C. So if I look at my Venn diagram, I've got this part of A that is a part of the set B as well, but not in C. But then I also have a region of A which overlaps with C, my red circle. My C circle got a little bit erased here, so let me try and quickly add that back in. So here was my C circle. Right? And there is, in fact, a part of A that overlaps with C. This overlap here in the middle would be those thefts that are justifiable. And if I grant that Q is true, then that must mean, I'm going to put a little asterisk here in the middle, that must mean that A intersect with C is not an empty set. So that's another way to translate that premise into logic. A intersect C is not empty. So this asterisk that I just drew in here is an element of the set A, and it's an element of the set C. This is probably Jean Valjean stealing a loaf of bread, right? It's a theft that is justifiable. And this premise is granting that such a thing exists. So there is some element sitting here in the intersection of A with C. Okay, so now I've completely labeled my diagram, right? And by having erased a part of it and drawn a little asterisk in here, this has gone from what we would have originally called a Venn diagram to now we call it an Euler diagram. Euler being a famous mathematician that has his name on so many things across the world of math. So now that we've labeled this diagram in such a way that it indicates both of our premises have been accepted, now let's assess the conclusion. Is it true that some immoral acts are justifiable? And I'm going to translate that into the language of set theory so that we can understand what we're really asking ourselves here. Some immoral acts are justifiable. Well, the immoral acts are the elements of the set B. Some element of B is justifiable an element of C. And just to get my color coding back in here, some green element belongs in the red set. Some immoral act is justifiable. Is that true based on the diagram? Is it true that there exists an element in my green B circle which also belongs to the red C circle? And I have to answer in the affirmative. Yes, it is true if we grant the premises P and Q, if we grant that all thefts are immoral and some thefts are justifiable, then it must be true that some immoral acts are justifiable. Why? This element that I labeled with a star here, that happens to be in the intersection of A, B, and C, is our proof of this existential claim. The claim that there exists an immoral act which is justifiable. And it is right here. So remember what this star corresponded to. This star was Jean Valjean. Apologies if you haven't seen Les Miserables, I recommend it. The movie is great, although Russell Crowe is not the greatest singer in the world, but if you can suspend your disbelief and think of his singing as more akin to heavy metal than it is to high opera, I think you'll still enjoy the movie. I did. But Jean Valjean is an example in literature of a theft which is seen to be justifiable, right? And so, according to our second premise, there exists an element of A which belongs to C. But, according to our first premise, every element of A is an element of B. And since there is an A which is a C, and every A is also a B, that means that there's a B which is also a C. And therefore, R must be true. So just to follow the line of reasoning again about why Jean Valjean is our proof that this is a valid form of argument. Jean Valjean is our asterisk in the middle of this diagram. So his theft in Les Miserables is an immoral act. Right? If we are accepting the first premise, is an immoral act, because that's by the premise P that says that all thefts are immoral acts, and therefore, in particular, his theft is an immoral act. On the other hand, some immoral acts wait a second. Some immoral acts are justifiable. Oh, sorry, some thefts. My fault. Let's try that again. Some thefts are justifiable. Right? That's our premise Q. And so the question is it true that there's some immoral act which is justifiable? Well, again, if all thefts are immoral, then everything which belongs to A must also belong to B. If some thefts are justifiable, it means that something that belongs to A must belong to C. But since everything which belongs to A also belongs to B, then we know that it will belong to C as well. So a better way to see this framing, and so I just kind of wrote this backwards. Jean Valjean is still our example that proves the case, but let me just review why that is a little bit more carefully. So because we're accepting premise Q, Jean Valjean was our example of a justifiable theft. Right? Some thefts are justifiable. Let's just say that that's the example. So his theft is justifiable. Right? If we read literature in that way. But according to premise P, every theft is an immoral act. Because it was a theft, is also an immoral act. That's by premise P. Right? But then that means that not only is that theft immoral and justifiable, it means that there exists an immoral act which is also justifiable. Right? So that element existing in this intersection is proof that this conclusion has to follow. So sometimes when you look at Euler diagrams in various sources, they don't always start as Venn diagrams that then get kind of erased and pared down. That's my preferred method to do it. But I want to close up the stream today by just showing what I think is a slightly more conventional way, maybe, of drawing the Euler diagram for this as we go. So here's an alternative way to sketch the argument that we just made. Instead of using a Venn diagram with 3 circles in it, which I still prefer, another way is as follows. Sorry, I gotta clear up my canvas here. So how this will usually look, and you may find that this is more straightforward, is I'm going to start by taking premise P, all thefts are immoral acts, and I'm going to draw it using 2 suggestively placed circles. And what I mean by suggestively placed is that here is my set of thefts, here is my set of immoral acts. Whoops. There's my set of immoral acts. And I've drawn it in such a way as to show that everything in A also belongs to B. Right? A is within B. A is a subset of B. That was the content of premise P. And now for premise Q, some thefts are justifiable. Right? So my thefts are A. And so there has to be something which belongs to both A and my justifiable set C. So that must mean that my set C has to overlap with A. So maybe I'll draw it like this. My set C must overlap A. And that's by premise Q, right? That says that some thefts are justified. So there's something here which belongs to A and also belongs to C. So then the question is it true that some immoral acts are justifiable? Is there something inside of B which belongs to C? And this diagram makes it plain. Yes, there's something that belongs to B that also belongs to C. Namely, this thing right there. There's Jean Valjean in this diagram, right? This element belongs to B because it belonged to A, and A is a subset of B. But we also know that it belongs to C, again, because we accepted premise Q. So this is a valid form of argument. If you tell me that all thefts are immoral and some thefts are justifiable, and if we both accept those premises to be true, then we conclude that we must also accept that some immoral acts are justifiable. The form of this argument is valid. The conclusion follows from the premises. We can debate whether the premises are true or not, and you'll certainly do that in your humanities type classes. But once we agree that both of those premises are true, the tenets of logical reasoning indicate that we must also agree that the conclusion is true. And that is what we mean by a valid argument. So we got to close up the stream for today. We had a chance to review 3 set Venn diagrams and how to use them to assess for the equality of 2 sets. So that was a big chunk of time. We spent like 40 minutes really getting our hands dirty with a couple of examples of how to stick together 3 sets using set operations and figure out whether 2 different expressions in set theory must represent the same set or not. And then we talked about how to assess a syllogistic argument, right, where we have a couple of premises and then a conclusion to decide whether or not the form of that argument is valid. And using a Venn diagram or an Euler diagram like the one we see here is a great way to do that. The hardest part about it, I think, is just figuring out how to arrange for the quantifiers to be satisfied. The all in this statement we expressed as a subset in our diagram, and the sum we assessed as just by placing a little asterisk somewhere that indicates that there exists one element of some set that belongs to another set. But hopefully this gives you some problem-solving tools to help you review for the exam. The exam is going to be posted tomorrow afternoon on Tuesday in Blackboard. You'll have the rest of the week to work on it. Your online homework system has a batch of review exercises for you to be working on this week to support your success in that, so continue to engage there. I will see you on Slack with any questions, and good luck with the rest of this exam.